Okay, so let's just revisit the last thing we did last lecture. If you remember, the derivation I was working on was the case where we had. Hang on a second. Let me just check the lights. Did those lights work? Those lights over there? Yeah, right. Okay, great. That's much better. Thank you. Where we were dealing with the problem where your initial point was fixed, but your final point had a value of the state that was given, but the time itself could vary. So the time at which you reach the endpoint wasn't determined ahead of time. And remember what I said was that when you start with the basic calculus of variations problem where both endpoints are fixed, the boundary conditions are given to you. So you have the boundary conditions. So you're not going to get any information out of endpoint variations because there are no endpoint variations in that basic problem. When you have a variation in the endpoint, now what happens is you get the condition that comes from the variation in the endpoint when the original problem statement didn't have a boundary condition in it, right? So in this case, what was free? TF was free. So because TF was free, I don't have a value of TF. I can't solve for it. There's another boundary condition that comes out of the first variation in the functional that provides you a different boundary condition. It has to be a different boundary condition for that endpoint. And if you remember correctly, for that particular problem, we said that the condition was that you get partial of L with respect to x minus d dt of the partial of L with respect to x dot equals 0. That's the Lagrange equation, or the Euler-Lagrange equation. And then you get this condition that you've got L of x of TF, x dot of TF, and TF minus the partial of L with respect to x dot times evaluated at TF times x dot at TF equals 0. So that's the boundary condition that comes out. And you can see that now that boundary condition is applied at TF, whereas the original problem statement doesn't have any boundary condition, doesn't have that boundary condition in it. This comes out of the first variation. So I want to do an example now just to show you how all this works. I mean, the examples are more of a way for you to be able to just see how the theory works in practice, but it doesn't really replace the theory. Because I mean, the thing about this class is fundamentally a mathematics course. I mean, optimal control is a subject of mathematics. It's not a subject of engineering per se. Engineering is an application of optimal control. People use it in engineering, but the actual subject itself has nothing to do with engineering. It's purely a mathematics subject. So let's just take this particular problem. I mean, this is a really simple example, but it'll help you kind of identify like how to if you had a problem to solve, what you would actually do. So in this case, the cost functional is the integral from 1 to TF of 2x of t plus 1/2 x dot of t dt. And the boundary conditions are x at 1 is equal to 4, and x at TF is equal to 4, and TF has to be bigger than 1, okay? So this is a constraint. TF, I mean, this integral doesn't make any sense. It would go backward if TF wasn't bigger than 1. So if you look at this, if you first apply the Lagrange equation, what you've got is if you take partial of L with respect to x minus d dt of the partial of L with respect to x dot, what do you get? Well, if I take the derivative of this with respect to x, what do I get? I get 2, right? And if I take the derivative of this with respect to x dot, what do I get? Sorry, this is a square. You get x dot. If you take the second derivative, you get you get this. So you get 2 plus x double dot. All right? Sorry, minus 2 equals 0. So this gives you x double dot is equal to 2. Now, it's a really simple differential equation. It says x double dot is equal to a constant. So x of t, you can directly see, is going to equal what? You integrate this once, you get a linear function of time. So you're going to get something that goes like t squared plus c1t plus c2. So that's the solution to that problem, where I don't know what the constants c1 and c2 are. So how am I going to get the constants? Well, the constants are going to come from the boundary conditions. So I know that x of 1 is equal to 4. So that says that 4 is equal to what? It's equal to 1 plus c1 plus c2, right? Because 1 squared is 1 times plus c1 times 1 plus 1. So, right? So that gives me one boundary condition. So this says that c1 plus c2 has to equal 3. So that I only have one equation there, so I need another equation. So the other equation comes from the boundary condition that you apply at the final time. So if you do that, if you apply that boundary condition, you get the following thing. You get 2x of tf minus 1/2 x dot squared of tf. And then and that equals what? Well, it equals 2 times tf squared plus c1 times tf plus c2. And then you get plus 2 times tf plus c1, and that whole thing has to equal 0. So if you solve these two equations, you've got to make sure you solve these equations properly. Of course, if you take the final solution to this gives you x star of t is equal to t squared minus 6t plus 9, and you get tf is equal to 5. So you can work out that solution yourself. That's a simple problem that comes up commonly. Let's do the last case, and the last case, which is sort of the one. These are the basic cases, which is, let's suppose again you've got the initial point fixed, but now this time what you've got is TF is fixed, so TF is here, and your final solution has a state or a value of x that can change. So in this case, what you've got is x of t0 is equal to x0. You've got x at tf is free, but tf is fixed. And the variation, or the cost, the functional itself, is equal to the integral from t0 to tf of L of x of t, x dot of t, and t dt. So now how are we going to do this one? We got to take the first variation in this cost functional and set it equal to 0. So what is the first variation in the cost functional? It's the variation in this. So how am I going to take this variation? How am I going to do it? Any idea? What do I need to do? What is changing in this particular case? So the endpoint times are now fixed in this case, right? So in this integral, what is not changing? T0 is not changing, right? Because it's fixed. TF is also not changing, right? So when I take the variation, I don't have to worry about the variation in the endpoint times, right? In T0, in these two parameters, T0 and TF, because neither one of them is changing. So I can immediately put the variation inside the integral, right? So this gives me the integral from T0 to TF of the variation in L dt, which we know is the integral from t0 to tf of the partial of L with respect to x times the variation in x plus the partial of L with respect to x dot times the variation in x dot, and then this whole thing is integrated over time. Now, if you look at this, you say, well, it doesn't look any different from the first problem that we did, which has fixed, which had fixed endpoints. But let's go a little bit deeper. So I know that if I integrate by parts on this second term over here, what do I get? So I get the variation in J is going to equal, well, it's uv minus the integral of v du. So what do I get? I get the partial of L with respect to x dot times the variation in x evaluated at the endpoints, t0 and tf, minus the integral from t0 to tf of d dt of the partial of L with respect to x dot dt plus the integral from t0 to tf of the partial of L with respect to x times the variation in x. There's a variation in x there. dt, right? So does everyone understand where that came from? When I integrate this by parts, I've got u dv. So I get uv evaluated at the endpoints minus the integral of v du. V in this case uv. V is the variation in x. Du is d dt of the partial of L with respect to x dot. So that's where this term comes in, but there's a negative sign because the integration by parts gives me a negative sign, and then I've got this over here. So this is equal to the partial of L with respect to x dot times the variation in x, the whole thing evaluated at tf, minus the partial of L with respect to x dot times the variation in x evaluated at t0. And then I've got plus the integral from t0 to tf of the partial of L with respect to x minus d dt of the partial of L with respect to x dot times the variation in x dt. This is a slightly simpler case from the one that we had before, right? But so if you look at this now in this case, you've got to see, you'll see that again, this is 0 because the variation in x at t0 is 0 because x is not changing at the initial time. So the only thing that changes in the boundary conditions is what's here. So what you get is you get the partial of L with respect to x dot evaluated at tf times the variation in x at tf, and then you get plus the integral from t0 to tf of the partial of L with respect to x minus d dt of the partial of L with respect to x dot times the variation in x dt. Because this is 0. Now, what's going on at the endpoint here? Let's look and see what's going on at the endpoint. I know that the variation in x0 is equal to the variation in x at t0 plus x dot, well, this is approximately, times what? Times the variation in t0, right? So actually it's the variation in x. It's x dot at t0 times the variation in t0, right? That's the condition that we have for the variation at the end. Sorry, it's a tf. Mistake. It's a tf. Okay? So that's the condition that's what's happening. Did I erase the picture? Yeah. That's what's happening up here, all right? If you remember the picture that I drew, this is always true. But what is fixed, or what is 0 in this equation? If I write this down, what's true in this equation for this particular case? What's that? This is 0, right? Because the variation in TF is 0, right? And you can write that. And you can say variation in TF is equal to 0, which is why that term is 0. So what this says is to first order, delta xf is delta x at TF, right? So I can replace this with that condition up there. So it doesn't matter whether I use this or I use that. It makes no. I can use either one in this particular case. So what what is the condition at TF? What must be 0 at TF? Because this is not 0 at TF, right? You can see that the value of x at TF can change, right? Because I can take a curve that takes me to this point. I can take another curve that takes me up to this point. The values of x at each of these points, on each of these curves, is different at TF, right? So the variation in x at TF is not equal to 0. Because if it were, the value would be fixed at that endpoint, which it's not, right? It's allowed to move along that vertical line at TF. So given the fact that it's not 0, what has to be 0 in order for this variation to be 0? So I'll write it over here, actually, so we have a little bit more room. So this is where you have to get an understanding of boundary conditions, because the boundary conditions govern so much of what's going on in these problems. So we can say, we know that the variation in x at TF is not equal to 0. But the variation in j has to equal 0 for a stationary point or stationary solution, which we also call in calculus of variations an extremal solution. So if the variation in j is equal to 0, it means that this whole thing has to be 0. It means that the partial of L with respect to x dot times the variation in x at TF plus the integral from T0 to TF of the partial of L with respect to x minus d dt of the partial of L with respect to x dot, this whole thing times the variation in x dt has to equal 0 for all variation in x at TF and variations in x at t. No matter what those variations are, this thing has to equal 0. What's the only way that that can equal 0? So that requires that the partial of L with respect to x dot at TF has to equal 0. Now, it tells you that the derivative of the Lagrangian with respect to the rate of change of the state has to equal 0. And what else? And this has to be true. Does that make sense? Is anybody confused at all about this? So the key thing in doing this is really important. This is what makes calculus of variations hard, is that the variations that you're taking at the endpoints are not, there's a sort of an intuition as to what you think they are, and then there's what they really are. What they really are is you're saying that I have a trajectory. I have a function. In this case, that function is x of t. I'm allowing that function to vary. And what I'm doing is separately, I'm allowing the function to vary across the entire interval, where I'm saying that there's a function, x of t, I'm allowing it to change across the entire interval. Then there's the variation in that function at the endpoints itself, which is separate from how the function varies across the interval. Those two things are not the same thing. I can have a function, just if you think of it without a variation, you could think of a function that x of t. I can take any function I want, and I could say that it has to take on, its endpoints have to behave a certain way. How its endpoints behave is separate from what it's doing across the entire interval. Okay? They shouldn't be coupled to one another. They're coupled to one another in the fact that it's the same function, but how the endpoint actually behaves is done separately from how the function across the interval actually behaves. So you can see when these boundary conditions are applied, that's exactly what winds up happening, is I get one condition that's actually a path condition, if you want to call it that. This is this differential equation, which is this Lagrange equation, which governs what's happening along the path. and then I get other conditions that govern what happens at the endpoints themselves. And those boundary conditions have to be done very carefully by going through the particular calculus of variations for that particular case, which is why when you solve problems, there are two ways to do this. There's what I call the undergraduate way, and then there's the graduate way. All right? The undergraduate way would be as follows. You look up the case in the book, and then you plug in and solve. All right? And you'll learn nothing in the process of doing that. The graduate way is to start from first principles and work your way through the variations, and then see what the boundary conditions are for the situation for the variational problem that you're trying to solve, and see how you got the boundary conditions, and then solve the problem that you're interested in solving. You'll learn a lot more if you do it the second way than if you do it the first way, because the first way is just a lookup table. I'm in Roman numeral 1, case A, subsection E, and I plug into this result. That doesn't teach you anything. It'll get you the answer to the problem that you want, but if you make a mistake, you won't understand why you made the mistake. And therein lies the problem, is that when you have a more complicated problem on your hands, it's not going to be one of these simple things that you can just look up in a table. You have to actually go through and really figure out, well, what is it? What's going on for my particular problem? I have to really understand that. And if you don't have the first principles to back up to, then what winds up happening is that you just find yourself plugging into formulas. And then when you plug into formulas, you don't know where you start. You started in the middle. You started with somebody else's result and just plugged in, rather than going from the beginning and saying, aha, I understand where the problem is. The problem's here. I made a mistake in this variation right here. If you just plug into a formula and it's all wrong, you'll have no recourse to be able to back up and be able to say, oh, that's why this isn't working out. And you can see these boundary conditions change a lot if you just change the situation. I mean, in this particular case, I'm fixing TF. In the case I had before, I was fixing X at TF, but I was allowing TF to be free. So just changing something seemingly small makes an enormous difference to not only the complexity of the boundary conditions, but sort of the character of the boundary conditions themselves. So this is a purely derivative boundary condition, whereas the one that I derived before was an algebraic plus a derivative boundary condition, right? Because it had a constraint which was directly on L and not on the partial of L with respect to X dot. So this is a very it's a difficult thing to teach in a sort of plug. It's not something you can teach in a plug and chug kind of way. You teach the concept of a variation, and then you have to understand what all these variations mean and how things are actually changing. So the very first thing I would do in any problem that you're trying to solve is ask yourself the question, what is changing? Because something is always going to be changing, right? And you have to say, well, what is that thing? I've identified for you in these particular cases what these things are. In this case, the value of X at TF can change. In the case I had before, the value of TF itself could change. So that's important. And in particular, you know that X of T has to change, right? You have to be able to vary X of T. If you couldn't vary X of T, then there couldn't possibly be more than one solution to the problem, because there's only one function that actually minimizes your cost. So that is not a very interesting problem. So clearly, X of T is going to vary. So this condition is going to wind up coming out in all these basic calculus of variations problems regardless. But even though it's going to come out, I think going through the steps of actually deriving it by going through the integration by parts and seeing that that's what you get, that sort of repetition gets you to understand that that's a common feature in all of these problems. And you're still not plugging into formulas. You're still going back to first principles to do this, okay? So it's not so simple just to say, oh, I got a lookup table. Because sometimes it's very tempting to just plug into lookup tables, because you're like, oh, well, how hard can this be? Somebody's already derived it for me. But the point of this class is for you to understand optimal control. If you want to understand optimal control, you got to understand calculus of variations. Because when we get to the optimal control problem, this is going to get really complicated. I mean, there are going to be so many variations that you're going to be like, that's just everything is varying. It's like, how do I keep track of all this? And it's like, well, then you got to fall back on your first principles. If you don't have those things, you cannot derive necessary conditions for optimal control. There's one other thing I want to talk about, which corresponds, which sort of relates to these boundary conditions. You can see that the boundary conditions always occur as a product of things, right? There's something times a variation in the value at the endpoint, right? In this case, since TF was the only thing, that's the only endpoint where something was changing, that there was a variation in X at TF. Notice that the first variation in J equaling 0 means that the product of these two things has to equal 0. So what I do is, if you go back to a basic thing that you've learned before, but I'm going to take this aside just to do it because it's really trivial, but I don't think it's something that people think about a lot. So I want to talk about it. If I say that I've got A times B equals 0, this is just a standard multiplication. If I say A times B is equal to 0, what does that mean? It means either A is 0 or B is 0 or both of them are 0, right? It does not say that you can pick the one that you want to be 0, right? Well, I want A to be 0. No, you can't do that. It says the product is 0, right? If they're scalars, right? If they're vectors, this gets more complicated, right? Because if I take the dot product between two vectors and I say they're 0, it doesn't mean either of the vectors is necessarily 0, right? It means that their dot product is 0. So this is a scalar problem. I'm dealing with just numbers here, right? Or functions, if you want to call it that. What it says is it says either A is 0 or B is 0 or both A and B are 0. So if you relate that back to these boundary conditions over here, you can see that the boundary condition doesn't necessarily say that this is 0. I said over here that that was 0, right? But I deduced it from something else. What did I deduce it from? I deduced it from another fact. I did not just immediately say the partial of L with respect to x dot evaluated at TF is equal to 0. What did I do? I said that what did I do? Right, I had to say that this was not 0, right? And the reason this was not 0 is because I'm allowing that value to be free. So the other thing has to be 0, right? Because the product has to be 0. If the other thing's not 0, by definition or by necessity, the other thing has to be 0, right? So it's really important. Now, if you change the problem ever so slightly, go back to the more basic problem. You remember in the more basic problem, the value at the final point was fixed, right? So if you look at that set of boundary conditions, you still get this boundary condition at the final time, right? You get this product of these two things. But in that particular case, what does it say? I don't know whether this thing is or is not 0, but I knew that if the final point was fixed, that the variation in x at TF is 0, right? Because it can't change, right? So therefore, because that's 0, that boundary condition automatically dropped out of the problem because I'm multiplying the partial of L with respect to x dot at TF times something that is known to be 0, and so it doesn't matter what that boundary condition is because it's going to disappear from the problem. But there's another boundary condition in that problem. If you go back to the basic calculus of variations problem, I said that x at TF is equal to xf. So even though I don't have this boundary condition here, which comes out of the first variation, I have a boundary condition from the original problem statement, right? So either way, I wind up with a boundary condition. I just wind up with a different boundary condition based on the fact that one thing is free in one case and that thing is fixed in the other case, right? In the case of the basic problem, variation in x at TF is fixed, but I already have a boundary condition from the basic problem on x at TF. In the other case, I have variation in x at TF is free, which is the one here, and the partial of L with respect to x dot at TF then is 0 because that other variation is not 0. Okay? So you have to go through this really, really delicately when you step through these problems to understand what variations are being allowed so that you can say that that's the boundary condition that I need to apply because it's being multiplied by something that's not 0. Okay? That's really important. Now, I'm not going to go into a derivation of this today, but I want to talk a little bit about, let's start with the first thing, which is just sort of getting ourselves beyond scalars, which is that all of this stuff applies to vector functions as well. So we have to have some kind of standardization for notation that we use when we deal with vector functions. So the first thing I want to do is I want to talk about dealing with derivatives. Because when you take derivatives of scalar functions, like if I have a function L, which is a function of x of t and x dot of t, and x is a scalar, the partial of L with respect to x and partial with respect to x dot are all scalars. Everything's a scalar. It's a very simple situation, right? But in the case of vectors, we have to have notation. So we have to. So this is the notation that I use for vectors. Now, for vectors and vector derivatives, this is not the notation everybody uses, but it's pretty standard notation. So the first thing is this: is we denote a vector x, which is an element of Rn, as we say x is x1 through xn, and this is the same thing as saying a column vector. So we deal mostly for the purposes of like handwritten notation, we always take vectors to be column vectors. They don't have to be column vectors, right? But we're gonna do this. We could use row vectors as the convention if we wanted to. We're not going to use row vectors as the convention. And then we say that x transpose is the transpose of x, which is a row vector, which is x1 to xn. Now, when we have functions of these things, so if I say f is a function of x, where f is a mapping that goes from Rn into R, right? So it takes vectors in n dimensions and it maps me to real numbers. Then what we do is we construct this thing called the gradient. So the gradient of f of x, it's not a vector, it's a scalar, is given as follows. We say the gradient of f of x is equal to the partial of f with respect to x1, partial of f with respect to xn. So it's a row vector. So this convention, you've got to understand. X is a column vector. I'm going to treat it as a column vector. When I take its derivative, I'm taking its derivative this way. It actually turns out that that's not the way it works. In actual geometry, if you were actually going to look at this in sort of a sense of a rectangle and a cube, that's not actually the way these derivatives work. The way these derivatives work is that you actually take the derivative this way, but nobody writes this way, right? Because there's nothing to write on over here, right? So you actually take the derivative. You say df dx1, df dx2, df dx3, all the way out to df dxn, which is sitting out here. And then when you take, then that gives you a row vector. And then what you do is, if you want to take the derivative of that, you take the derivative this way, right? So you wind up with a rectangle like this. But you can't write in 3 dimensions, so that's why we do it this way. This keeps us in the board, right? Because we don't have the ability to write in 3 dimensions. We write in 2 dimensions. So this is the first derivative. Now you got to understand that that's the first derivative, but the second derivative follows a slightly different convention. So we say that we call it the Hessian of f, and it's denoted as follows. We say it's del squared f of x, and this is equal to the gradient of f of x transpose. So this is equal to the gradient of this thing, the partial of f with respect to x1, partial of f with respect to xn, and then this gives me is equal to d dx1 of the gradient of f all the way out to d dxn, the gradient of f. So again, you notice what we did. We first flipped it to a column vector, and then we took the derivative again that way. We're always taking derivatives that way, right? Or across. We're not taking them down. All right? So that's the standard convention for this. Now, in the case of a vector function, so suppose now that f of x is a vector function of x, where f is a mapping from Rn into Rm. So what this looks like is we say f of x is equal to f1 of x up to fm of x. Then the gradient is simply just the derivative of that, which is, so we say the gradient of f of x is called the Jacobian of f of x, and it's equal to the derivative this way. So we take the derivative of this with respect, so we take the partial of f1 with respect to x1, partial of f1 with respect to xn, and then we take the partial of fm with respect to x1, partial of fm with respect to xn. And for the purposes of what we do in this class, we don't go to higher dimensional derivatives. When we go to higher dimensional derivatives, you got to do other things. So that's a different story. Okay? So that's the standard convention. That's the standard notation. Why this becomes important is because in any process that we would like to really study, typically they're not governed by scalars, right? The functions that we're dealing with are not scalars. If you think of a system of differential equations that governs the motion of some process, right? That's typically not going to be a scalar differential equation. It's going to be a vector differential equation, which is going to have multiple components to it, and those multiple components are typically referred to collectively as the state of the system, right? So the state of the system is typically not a scalar. So what we have in optimal control is we deal with problems of this form. Well, I'm not going to write the whole problem, but let's talk about the differential processes first. So the components of an optimal control problem are as follows. First thing is we have dynamics. So we've got these differential equations. So typically we write these as in the following form. X dot equals f of x of t and u of t. And it also may be a function of t, but it also might be a function of some other parameters, q, where q are a bunch of static parameters. This is a very common formulation. We normally in physical processes, we can write things in that form. And the reason we can write them in that form is because this form of first-order differential equations is actually motivated by typical physical systems which may be governed by Newtonian mechanics. F equals ma, right? If you say F equals ma, a is acceleration, which is second derivative of position. The second derivative of position can be written as the first derivative, dr dt, is equal to v, and then dv dt is equal to f over m. So you wind up taking that second-order system, and you write it as two first-order systems. So you ultimately can write it as a first-order system. So that's how we start this. Now, when we do this quantity x of t is what's called the state of the system. And u of t is what's typically referred to as the control or the input. Okay? Now, the distinction between these two things is that, and then I forgot about q. Q is static parameter vector. What I mean by that is that q is not a function of time. Q is just a bunch of static parameters. They can take on just numerical values, but it's not a function of time. But nevertheless, it could change. It's a free variable that can be changed, but it can only be changed. It's an isolated numerical value that can change. Now, if you look at this, you'll see that the state is a process that's controlled by the control. The control is the thing that you can choose. I can say, well, this is what I want the control to be. I give you a control, and then it'll tell me what the process actually does. So typically what we would also be given, these are the dynamics. The next thing we would be given is we would be given boundary conditions. Now, the boundary conditions are similar to what we've seen in these scalar problems, except for we write them in a more general way. We say we've got a function phi, which is a function of x of t0, x of tf, and tf, and it may also be a function of q, and that is equal to 0 if we just deal with equality boundary conditions. Now, the function phi tells me collectively what has to happen at the endpoints in the problem. All right? It could be very complicated. It could be very simple. It could be as simple as x of t0 equals x0, which is what I showed you in the basic calculus of variations problem. That is about, so this function tends to cause people a lot of consternation because they're like, wow, that looks just really so general. Well, what's so general about it? I'll give you an example of here's something that you all know, and I can write it in this particular form, and nobody would get upset if I did this, right? If I say x of t0 is equal to x0, and I say x of tf is equal to xf, you say, well, that's not in that form. This is not in that form, right? But if I rewrite it, I can write x of t0 minus x0 equals 0, and x of tf minus xf is equal to 0. So what's my function phi? So phi is equal to x of t0 minus x0 and x of tf minus xf. That's phi. Right? Now, that's a simple boundary condition. These are what we typically refer to as simple boundary conditions because you're directly constraining the initial value of the state. But it may not be that you want to directly constrain the initial value of the state. There are so many applications where you don't want to constrain the state itself, but you want to constrain a function of the state, right? This comes up in mechanical engineering. It comes up in aerospace engineering. I'm an aerospace engineer, so I tend to look at things from an aerospace perspective. But think of a problem where, for those of you who know anything about spaceflight dynamics, think of a problem of transferring a spacecraft between two orbits. You want to go from one orbit to another orbit. All you care about is that I have an initial ellipse that I'm going to start in. Let's just assume we're around a planet. I have an initial ellipse. I have a final ellipse that I want to go to. I'm not telling you where on that ellipse you need to be. I'm just saying you need to start somewhere on this ellipse, and you need to finish on this new ellipse, right? So you could have a problem where you say, start me at whatever point you want to on this ellipse, because there's going to be more than just boundary conditions. But right now, what I'm just dealing with are boundary conditions. Let's just suppose I had the problem of transferring a spacecraft, let's say from an orbit that looks like this to an orbit that looks like that. So the spacecraft is sitting here in some orbit, and it can be anywhere on the orbit. It just says, tell me what the path is that takes me from this orbit to that orbit. I don't care where you start on this orbit and where you end up on this orbit. Just take me between these two orbits. So that I start on this path where I'm going around the planet here, and I wind up going around the planet here. I'm just making up a problem. I mean, it could be anything. But the point is, the value of the state is not constrained here. It can be anything that lies on this curve. It can be anywhere on this curve. So it's not that particular value of the state that I'm concerned about. I'm concerned about the function that keeps me on this curve. That's my initial condition. It says my initial condition can be anywhere on this curve. My final condition has to be anywhere on this particular curve. So they're not fixed values. I can start somewhere. I could start over here, and I could find some trajectory that takes me to this other curve, and it takes me here. I don't know what the path is that's going to get me there. All I'm saying is that you got to start on this curve, and you got to end on that curve, right? The curves are spatial, right? They tell me that this is a locus of points that defines where I can be when I start my orbit transfer, and this is a locus of points that defines where I can be when I finish the transfer. But it doesn't tell me where on those locus of points I have to be. If I have this particular type of boundary condition, it says the initial condition has to be this particular value. So that's a point-to-point problem. This is not a point-to-point problem. It's a locus-to-locus problem. And that function that I've written here allows for formulations which take me from one locus of points to another locus of points. So this is a more general formulation of boundary conditions from this over here. This is much more restrictive. I cannot do anywhere near as much with this type of boundary condition as I can with that type of boundary condition. So this allows a lot more freedom and a lot more flexibility. It opens up the space of problems that you can actually solve by formulating your boundary conditions this way. So now I have two things. I've got dynamics and I've got boundary conditions, and I've got this thing called control, which I can actually change. And I could say, well, I want the control to be something to affect what's going on. So now, if I say that I want to satisfy a bunch of boundary conditions, and I want to be able, and I have these dynamics such that these boundary conditions are going to be satisfied, but I've got this control, how many solutions would there be to this problem? In other words, in general, would there only be one control that could take me from, that would satisfy those boundary conditions? There may be many controls that take me there, right? So the point is that which of those controls do you want to use? You may have an uncountably infinite number of functions that you can actually use that satisfy the boundary conditions that take me from point A to from one locus to another locus, right? The point is, you don't know which one you want to use unless you put on there some kind of a performance metric and say, this is the metric that tells me whether my solution is good or bad, right? Or better or worse, right? So then what we do is we construct what's called a performance index. And so the performance index is made up of two parts. It's also called a cost function. We call this performance index J, which is the same thing that we had before, but it now consists of two things. It consists of what's typically known in the calculus of variations as the Mayer cost, which is this part of the cost right here, and what's typically known as the Lagrange cost. Now, if you look at this, you'll say, well, that looks a lot like what we had done with the basic calculus of variations problem. This tells me, as I move along the path, the integral tells me, how does the cost increase? It's going to accumulate, right? There may be something that I'm incurring as a cost as the process actually evolves. This first term over here tells me what's the cost of being at the initial or the final point. And you can think of this in many different ways, but let's take another aerospace problem, because this is a really easy one for somebody to think of, which is clearly, as you fly a spacecraft or as you drive a car, you're going to be consuming fuel. So as you move along the path, you're going to be burning fuel, correct? So the rate at which you burn fuel depends upon the characteristics of the engine and everything, but you will be burning some fuel. So unless you just get lucky and you happen to be just on a coast going downhill or something like that. But generally speaking, when you're doing one of these things, you're going to burn fuel. Given that you're going to burn fuel, the question is, well, if your metric is I want to conserve as much fuel as possible, I want to use the least amount of fuel, then your cost has to reflect what that would be. So in the case of, say, a spacecraft, you normally have an equation that governs the rate at which fuel is burned, which looks something like this. And this is the mass flow rate. And so what happens is, if you look at m of t, if I assume all the things in here are constant, you get the integral from t0 to t of so this is thrust, t over ISP times g0 dt. So you could see that if my cost metric was to minimize the amount of fuel burned, I would want to make what? What would I want to do? Well, this is going to, sorry, there's another term. M at t0. So I would want to burn as little fuel as possible, so I would want to make this quantity, what? I would want to make it as large as possible, right? So when I got to TF, right, if I put TF in here, this quantity winds up being as small as possible. I mean, as large as possible, right? So I'd want to maximize this, because if I want to burn as little fuel as possible, I want the mass at the final time to be as big as it possibly can. So I would want to maximize this, right? So the performance index could be a minimization, where you want to say, where you pose it as, I want to burn as little fuel as possible. It could also be a maximization, where you say, I want to have the largest amount of fuel that left when I get to the end. Either way, one's a minimization, one's a maximization, but they're the same thing. I can just write one as the negative of the other. If I want to write this problem as burn as little fuel as possible, I just take the negative of this and then minimize the negative. So maximization is the same thing as minimization of the negative, right? So this gives me a way of saying, if I choose a particular control, it tells me how good my solution is. Now, if you look at this in a very qualitative sense, and I'm going to stop after this, you could see that if I just started plugging in different controls, right, I could say, well, let's try this control, right? And then let's see how much it costs. Well, I could try another control and see how much it costs, and I could just kind of randomly keep choosing controls until I say, well, I've looked at a whole bunch of controls. That one looks pretty good. I'm going to pick that one, right? But that's clearly not a very systematic way of going about doing this, right? But if all you were doing was just playing with numbers and just plugging in, you could try it. But you'd have a problem on your hands. The problem is that just because you choose a control doesn't necessarily mean you're going to be able to satisfy these boundary conditions, right? So the boundary conditions come into play here. Just because I have a control, that tells me now I can integrate my dynamics. But if I integrate the dynamics, I may never be able to satisfy these boundary conditions. So many things are going on in these problems. I want to make that cost as small as possible. if it's a cost minimization problem, but I can't do it in just any old ad hoc way. I have to do it in some sort of a systematic way. So what we're going to do next lecture is we're going to start the process of showing how this particular problem can be transformed into a calculus of variations problem, and we're going to go through the calculus of variations for that and show how the optimal control conditions actually come out of the whole thing. We'll start that on Friday.